Okay, it's been a couple of minutes, so I think I'll get started. Let me share the screen. Um, During this, it's pretty casual, so feel free to ask questions in the chat, unmute and ask questions. There's also some built-in like practice questions throughout the PowerPoint. So to start off talking about physics, this is like the topics we're going to go through over this PowerPoint, but this is also like one of two parts. Wednesday's going to be the second part. So I'm aiming to maybe finish fluids or electrostatics. We might do more, might do less. We'll find out. And then this PowerPoint should be shared on the Canvas eventually. So just to overview physics on the MCAT and what it looks like. It's within the first section, the chemical and physical foundations of biological systems. And so that's like the first one you're going to do chronologically. And according to the AAMC, it should be about a quarter of that section. So you should really get like 15-ish questions about physics. There's also your periodic table provided, but you're not going to get any of the formulae. So you have to memorize the formulas. There is some like decay or stuff like that that revolves around the periodic table. It's like a very small part of physics, but at least you'll have the periodic table for that. And then obviously for chem. You also don't have a calculator, so you're going to need to do some mental math. I think something that also helps is like if you notice the answer choices are very far apart in terms of numbers, like just like even the amount of digits is different, round things if you have to, if the math gets too hard. Like if you have a number that's 190 that you need to multiply, just like round that to 200 and see where your answer ends up. And the good news is there's no calculus. So even though like the physics classes you've had to take are calculus based, you're not going to have to do any of that. So it's mainly just going to be like multiplication, addition type questions if there are numbers, or it could just be like more concept based questions. So in terms of units, I think units are one of the best things to understand for MCAT physics. It can help you a lot. So it's the questions are going to use the standardized units, the SI units, which are part of the metric system. And if all of your answer options have the same units, and then you're given some numbers with their units, sometimes you don't even have to know the underlying physics. If you just see it's like meters per second in the answers and you have a meter and you have a second, something like that, a lot of times you can already get a hint on what to do. So SI base units are the ones written just kind of in the center of the screen there. It's like meters, kilograms, seconds. And then it's also good to know how you can get to other units. Any other unit can be split up into the basic ones. So like, for example, a Newton is a meter times a kilogram divided by a second squared, things like that. So understanding the units can help a lot, especially when you might not be able to remember the formula. The prefixes are also good to know in terms of like a milli something is like 1/1000th. So like a millimeter is a thousandth of a meter, things like that. And then graphs. So you might be getting a graph with your question. In that case, you want to look at the information they give you. So like the title, the label on the axes, and usually units as well. And from a graph, the slope and the area under it can be very important. So like the slope is like the derivative, I guess, and the area under is like your integral. And you want to think about units when you're doing this. So if you have like a velocity per time graph, the slope of that graph is your acceleration because it's like your velocity divided by time. And then the area under it is your displacement because it's kind of like your velocity times time. So like if it were a rectangle, that's literally just those two numbers multiplied together. And you can also think about units and figure that out as well. So like the slope, the units of the slope is going to be meters per second divided by second, which is the same unit as acceleration. Same for like displacement being the area under. So a lot of times for graphs, you can get information that way. Okay, so to start off, we're going to start with kinematics. And at the start of each section, I just have like what the AAMC says will be part of it, like in their overview. The PDF name is written in the corner there. But this is kind of what this section is going to go over. So they're going to talk about translational motion and equilibrium. So Newton's laws, forces like friction and stuff like that, center of mass, all that. But to start off, just like kinematics in general, these are the kinematics equations hopefully you've come across in physics. One thing I like to mention about them is that all of them are missing one of your 5 kinematics variables. So in terms of the 5 variables, you have displacement, time, acceleration, initial velocity, and final velocity. Out of those 5 things, you will be given 3 if you're trying to solve for something. You're going to have to find one of them, and you can forget one. So if you look at like equation 1, for example, there's no displacement. So if you're given initial velocity, acceleration, and time, and you need to find final velocity, this would be the equation for you because it doesn't involve displacement and you don't have or need displacement. So it might be helpful to think of them that way, as like kind of just like a puzzle, and you pick the equation that revolves around the variables that you have or need, and you can just forget one. Because sometimes I've seen people kind of like try to use an equation and you don't actually need displacement, but you're like lost because you're using an equation that hasn't. So that might be good to know. So we'll do a practice question just to keep you guys engaged. I have some involved. Feel free to put the answer in the chat. If you don't feel like sharing, you can like privately send it to me as well. That's fine. And then maybe when most people have answered, I'll go ahead and show the answer. Yeah, thank you, Mackenzie. There's a great piece of advice in the chat that you can also brain dump formulas, and it works out as well because this is literally the first section. So if there's like the last things you want to memorize or like keep very short term on the car ride there or something, you can write them down during the section where you have to read the instructions and stuff, and you can write it down on like the spiral notebook dry erase that you get. So that's good. I've received some answers private message. So in the interest of time, I might move on this one. So the answer here is C. And so this one is, if we go back to the equations, you want to use the one here, the third one, and then your initial velocity is 0. So you can actually just like take out that term. If it wasn't, you might have had to use quadratic formula. So it's a good thing if that term goes away. So then you have like displacement is half at squared, rearrange, and then you can find that your time is the square root of 4, so it's 2 seconds. So questions like these, good to know the formulas, good to also see what do I have. So like starting from rest is a very key way to say your initial velocity is 0 and solve from there. Center of mass, another important concept, is basically just a weighted average. So you can see like the distance of your center of mass is if you take like the distance of every object multiplied by its mass and you divide it by the sum of all the masses. This also works for like the velocity of the center of mass, just replace all the x's with v's. And you can set anywhere as your 0, but be consistent. So you can set like the leftmost point as 0 and see how far everything is. Or if you're dealing with like a fulcrum or something and you want that to be 0, then things to the left are negative. Oh, I guess my video is flipped, but things to the left are negative, things to the right are positive. Whatever it is, whatever is convenient to set as 0, feel free. Just be consistent and put everything relative to that. In terms of forces, we have Newton's second law, F equals ma. F force and acceleration being the vectors there, so they have like the arrow above. Common forces are gravity, which is like mass times the gravitational acceleration, g. You also have the spring force, kx, so the spring constant times the displacement from the equilibrium position. Tension and friction. Friction, I think I talk about a little later. If you have a constant or 0 velocity, that means the net force is 0, since force causes acceleration. So if it's not accelerating, no force, no net force. So it could be like just equal forces in different directions. Torque is F cross R. You might have seen that formula. It's also I times rotational acceleration. The thing with cross products, which is good to know since it's F cross R, is you want like the perpendicular portion. Perpendicular meaning 90 degrees. So if you look at the kind of drawing I have on the bottom there, if you have a force at an angle and your lever arm is the R there, then it's going to be FR sine theta. And you can think of that as you're taking the part of the force that's 90 degrees to the radius, which is the middle drawing, or you could be taking the part of the radius that's 90 degrees to the force, which is the drawing on the right. So different things work for different people, maybe whichever one's like easier for you to visualize, but just know you're trying to look at the part that's 90 degrees. Since if two things are going in the same direction, if they're parallel, there's like no torque generated, and the maximum torque generated is when two things are 90 degrees. So that's cross product. More about another force, friction. It's going to be proportional to your normal force. And for static friction, it's that your static friction is less than or equal to the coefficient times normal force. For kinetic, it's equal to the coefficient times normal force. And the reason that for static it's an inequality is that it could be less than the maximum. So if it's equal, that's the maximum static friction you can have, but it could be less than that since it's just trying to counter what's going on. So if you see the graph there, based on how much force you're applying, your friction is going to increase as you apply more and more force. So as you're applying like 2 newtons, your friction is also going to be 2 newtons just to cancel that. But once you break the max static friction, that's when you're actually going to start sliding the object. And then that's where you get to kinetic. And then kinetic's going to be less than your applied because at that point your object's actually accelerating and moving. So another thing that might not be intuitive is that rolling wheels are static, whereas kinetic friction is for sliding. So the reason for that is like as a wheel rolls, only like one part is touching the ground at every time. So it's not like the individual parts of the wheel are not sliding on the surface, like the road or something, as it rolls. So that's good to know. Again, at any point, if you guys have questions, put them in the chat if anything's unclear, or unmute and interrupt me, that's fine as well. So moving on to the next part is work and energy. This is what the AAMC says you should know. So FD cos theta we'll get into, and then just kind of like the energy equations there. So for work, it's force dotted by distance. So we talked about cross product. Dot product is the opposite. You want the parallel portion, not the perpendicular. So for work, that ends up usually being force times distance times the cosine of the angle separating them. And you can notice in like where the red arrow is, you're basically taking the part of the force that's in the same direction as the distance. So if you're applying a force diagonally, but the distance it's moving is like horizontal, the vertical part of your force isn't actually contributing to the work since the distance is only horizontal. Work and energy, it's also important to note, are scalars. There's no direction to either of them. So like for a dot product, when you take a dot product, you get rid of like the direction. Energy is also scalar. So here is a question about work. feel free to drop your answer A to D in the chat. I'll give like 30 more seconds. Okay, yeah, there's a C in the chat. That is correct. So the 50 kilograms might trick you a bit. I think that's why it's there, but it's basically the 20 Newton force times the 10 meters. And since they're both horizontal, you don't have to take any like cosines or anything. There's no angle involved. They're in the same direction. Here's another one about work. This one's more like manipulating. This is more like pilot questions maybe you have seen that don't explicitly have numbers. Okay, so for this one, it's basically that the distance, like h1 and h2, the distance is doubling. So it's going to be d, since you're doubling the distance with the same force, it's going to be double the work. So moving on to energy, these are like the more common forms of energy you'll come across: kinetic, potential, and spring. So those are the formulas to calculate those. Work energy theorem is also important to know that work is change in energy. So if you have like the final energy of something and the initial, the difference between that is how much work was done, because that's how much your energy changed. Power is another important one. It is your work divided by time. So you might, push the same box the same distance, but if someone does it faster, then that's more power. Here's a question about power. Should be quick. Yep, so power is again work over time. So you're gonna need the work and how much time it was done over. Perfect. All right, the next section is thermodynamics. And this is what they say, but also at the top there it says GC in physics. So some of this technically falls under Gen Chem, like the bottom parts, but the more physics part is like the PV diagrams. So work is the area under or enclosed by a pressure volume curve. So if pressure and volume are your two axes, you can find work from there. Heat transfer is also good to know, which is going to be on the slide. And then coefficient of expansion. So PV curves, as I mentioned, if you're graphing pressure and volume, work is going to be the area enclosed there. That's pretty much what you need to know there. For heat transfer, the three types are conduction through contact. Convection is like the motion of fluids. A fluid is a liquid or a gas. So it could be air, or it could be like if you're boiling water, there's convection through there. Conduction to the pot on the stove, but then convection within the water. And there's radiation, such as like the sun's heat that we get. In terms of expansion, a change in temperature can change the length or volume of an object. So alpha is the coefficient of linear expansion and beta is the coefficient of volumetric expansion. I'm pretty sure they don't actually teach this during physics class, so this might be good to know. One, like the first equation you can think of as like a lot, A-L, they just kind of like an O-T. So your change in length is that coefficient times the original length times the change in temperature. It's likewise for volume. And also, if you only have one coefficient, beta is 3 times alpha. And you can think of that as like length is 1D and volume is 3D. So it's like 3 times that. If your length is changing a certain amount, then your volume is changing that like three times. So those are just good to know. Like I didn't think they were important, but like the volume one came up on my MCAT. So low yield, but could be important. The next section is physics, or fluids, sorry. It's all physics. For fluids, this is the main stuff you want to know. So it'll be on the slides here. So pressure, the first thing about pressure is hydrostatic pressure. So if you're anywhere in a fluid, there's weight of the fluid above you that exerts pressure, and that's rho GH. So the density times the acceleration due to gravity times the height. So the point that they're mentioning there, the height you're going to take is everything above that, and then all that fluid is exerting pressure on the point. So practice question here based on that. Okay, so we've gotten some private messages. So since you're just trying to take the difference between the 2 points, you only really need to think about the height difference between those 2 points. And so again, rho GH, so you have your 1000, your 10, and your 0.25 all multiplied together, and the units will also agree if you're trying to figure it out based on units. If you forget the formula, that would also work. And also in terms of multiplication, just like another trick, sort of, if mental math is part of the issue, is like thinking about what order you do the multiplication. So like in my head, I knew I had to multiply these three. I would do like the 0.25 and the 10. And I know a quarter of 10 is 2.5, and then multiplying that by 1,000 is just 2,500. So whatever order works, you might want to think about that as well in terms of answering these questions. Here's another one. All right, so for this one, similar stuff, you're gonna multiply them all together, and the answer is D there. All right. So moving on, another type of pressure is osmotic pressure. And it's this equation here, which I like to think of as like a spin-off of the ideal gas equation. But it's the equation as written is pi is IMRT. Pi is the osmotic pressure you're solving for. And then I is the Van't Hoff factor, which you can actually solve for yourself. It's just like the number of species a molecule will form when dissolved. So the thing on the right kind of shows it better. Is since sucrose doesn't dissolve, that's just one, because it's just going to be the one molecule. But for like NaCl, it's going to become Na and Cl when it dissolves. So that would be two, things like that. And then you'll also need the solute concentration, temperature, and gas constant. So basically you can think of like the IM as your number of moles divided by your volume, since you're dealing with like a concentration and you're multiplying by the number of molecules. So it's kind of similar to the PV equals nRT equation. And then P, of course, is the osmotic pressure you're looking for. Another equation, this one you've probably seen in physics, is continuity. And it's just that your area times volume is going to be consistent at any point. And that's because if you multiply area and volume, that gives you your flow rate. And so that has to be constant. If you're flowing a certain amount in a tube, the same amount has to be coming out. You're not like losing anything in the process. So if a tube narrows, it's going to, the fluid will move faster so that the same volume can pass in the same amount of time. And so the example here, you can see the volumes, the velocity is going to be faster in the narrow part, V2. Bernoulli's equation is another important one, and that's basically saying this sum here, so pressure, static pressure, dynamic pressure, and hydrostatic pressure, if you add all those up, it's going to be constant along a stream. And so static pressure is just like your capital P. Dynamic is, you can think of it as kind of like kinetic energy, which is like half mv squared, but instead you're going to use density. And then hydrostatic pressure you can think of as kind of like your potential energy, which is mgh, but again, instead of your m's, you use rhos, you use density. So that whole sum is going to be constant. So you can think of like if you're comparing two different points, then that whole sum on one point is going to be the same as the other point, which is what the bottom left equation is basically saying. And there's also this like Venturi flow meter that they sometimes use, and you can see there that like when the tube narrows, the speed's going to increase, and so the pressure decreases, and it's basically the column height is going to be different. So if you see a contraption like that, it's basically calling back to Bernoulli's equation. So here is a question about that. Yeah, okay, so it's going to be the point of maximum diameter, and this kind of combines the past two things we've seen. But when you're using Bernoulli's equation, when the velocity falls, that's also, since that's part of the kinetic energy part, let me go back. That's part of this term here, your dynamic pressure. So at your maximum diameter, that's when that's going to fall. And so you're going to need more pressure there. So that's basically, it kind of combines the continuity and the Bernoulli, since your high area is going to be low volume. And then when you have low volume, this whole sum still has to be constant and your height is constant. So you're going to have more pressure. That's kind of how that all combines together. Another thing related to fluids is surface tension. So low surface tension, you'll usually have like a higher surface area and weak attraction. Higher surface tension, there's strong attraction between the molecules, and you'll have a lower surface area. Water is usually one of the fluids they say has a higher surface tension. And that's why you can kind of form droplets of water. Another thing I just put in here, it's mainly Gen Chem, but in terms of gases, these are good things to note, like the gas laws and just the theories of gases. But again, I think most of this counts as Gen Chem. And so then we move on to electrostatics and magnetism. We're about halfway through. Let me know if I'm going too fast or too slow, or if there's any questions at this point. I'll give you guys a minute to look through this or drop any feedback in the chat. All right, so the next part, electrostatics and magnetism. So leading into more physics 2 content. What they want you to know about it is charge, conductors, insulators, Coulomb's law, and like electric fields. So again, just a lot of the physics 2 stuff you've seen, electrostatic energy. But also, again, as we said in the beginning, there's no calculus on this. So it's not going to be like your double integrals to figure this stuff out. You can just know like the basic multiplication division formulas. Also in terms of magnetism, the definition of B, the magnetic field, and if things are moving in magnetic fields, your Lorentz force. So as I mentioned, units are pretty important. Since you're not using calculus and stuff, units can be very helpful in terms of electricity and like electrostatics. So in terms of units here, for Coulomb's law, and the force and the electric field, if you look at the equations, force is kqq over r squared, whereas electric field is just kq over r squared. They put like a capital Q to indicate it's like your bigger charge, but the real only difference is one Q. There's two Q's in Coulomb's law and only one Q in the electric field. So based on that, it makes sense that F is equal to EQ. Like if you just multiply by the other charge, you'll get the force. And that's also kind of the definition of an electric field. It's like what force an arbitrary charge would feel if it were moving there. So if you put in different charges of things, they're going to feel a different force, but they're going through the same field. So if you take that field, multiply by the charge that you're putting in it, you'll get the force that it experiences. So things like that. If you know the base formula differences, then you can also figure out how to get from like one thing to another, like F to E. Potential energy is kqq over r. So then you can see the difference between force and potential energy is just that radius in the denominator is squared in the force, but not in the energy. And that ties back to what we know about like work is like force times distance. Energy is, the change in energy is just the work. So if you just multiply by a distance, you can move from force to energy. So just like concepts you've already maybe seen in like physics 1, but now applying it to electricity. Another thing for electric potential. If you look above and below, so like the third and fifth equations there, U is KQQ over R, V is KQ over R. So just like force and electric field, the difference is just a Q. So U divided by Q is V. So things like that. Knowing the difference between the equations can help you move between the different variables you have. Okay, and so for electric field lines, if you had to draw them, it's like positive spreads good energy, so it's like outwards from positive, whereas for negative, it's like towards the negative. So if you're drawing electric field lines, but if there's like two things, one's positive, one's negative, it'll be moving from the positive towards the negative. And if something's neutral, there's no electric field lines there. So if you get a question with like field lines drawn and you have to know what the charge is, if it's towards it, it's negative, outwards is positive. In terms of magnetism, again, there's like a bunch of equations. The main thing they talk about is the Lorentz force, which is like the force if a charge moves in a magnetic field, and that is the QVB sine theta. And so sine being because you want the perpendicular part, kind of going back to like when we were talking about torque and cross products. And so Q is the charge, V is the speed, and B is the magnetic field. And if those things aren't all 90 degrees from each other, so charge doesn't have a direction, but if the speed and the magnetic field are not already 90 degrees, you want to take sine of the angle between them. If they are 90 degrees, then sine of 90 is 1. So that's why. And then magnetic field can also be derived from equations on the left there, based on if you have like a straight wire or a loop, but similar equations. And then you just need to know the force as well. Another equation for the force can be ILB sine theta, and that's if it's a current carrying wire. So that I is your current, L is like the length, B is the magnetic force. So those are good to know. Moving on to circuits. This is the stuff that's like important about circuits, I guess, the stuff you should know. Current is just charge over time. So I is the symbol for current, and it's your change in charge over your change in time, measured in amperes. And then you also want to know your EMF, electromotive forces, also known as voltage. In terms of resistance, the most important one is Ohm's law, which usually is written as V equals IR, but also here it's written I is V over R. You want to know the difference between resistors if they're in series or parallel, resistivity, which we'll get into in the slides, capacitance, conductivity, and the different meters, which are also in the slides. But again, a lot of physics 2 type content. So one thing to know is Kirchhoff's loop and junction rules. So the loop rule is more about voltage and the junction rule is more about current. But what you want to know is like across any loop in a circuit, the sum of the voltage has to be 0. And so in terms of summing, if you're gaining voltage, that would be like a battery, that would be positive. But if you're losing it, you're going to do negative. So like for the examples here, I took this from like my physics 2 class notes, but in the bottom there, the number 1, the battery, that's going to be an add of voltage, so that'll be a positive number. But then I guess you'd use IR to find the voltage lost, the voltage drop in resistor 2 and then resistor 3. So you might have like V of the battery minus IR for resistor 2 minus IR for resistor 3. The whole thing's going to go to 0. So in every closed loop, whatever voltage you're adding is also dissipated or lost over the loop. And then the junction rule is that your current in has to equal your current out at any point in a circuit. And so if you're looking at the actual photo there, you can choose what you define as in and what you define as out, but the sum has to be 0. So if you have something current going in one way and then splits into 3, the sum of those 3 out have to equal what was put in. So charge doesn't build up in your wires. So here's a question about that. Also, if you're not familiar with the term, terminal voltage of the battery is like the voltage coming back to the battery or used within the battery. So you can just think of like how much is the battery providing minus how much is used. That'll be the hint for this one. All right, we've gotten some private messages. So yeah, it's going to be B here. So basically you have the battery voltage, the fancy E there, and then the voltage to overcome that resistance they're talking about is IR. And so to subtract the two, that's going to be your, so E minus IR is going to be your terminal voltage. Here's another question. This might maybe require a bit more time to solve. Okay, so this one, I'll try to annotate and also go through how I would approach it. So the first thing we see is there's like this junction here. We're given information about the 2 ohm resistor, and we know that there's 2 amperes of current going on here. And in terms of the junction rule, we know whatever current went in here has to equal the sum of what went out. So it's that 2 amperes plus however much current is here. If you add those together, that's going to be the current going through your 3 ohm resistor. This is just kind of extra stuff to maybe distract you. But what we really need to do is just solve this area here. What's important to note, I guess I don't have it explicitly on the slide, is that in series, your current is the same. In parallel, your voltage is the same. So if you have like a lot of resistors in series, the current traveling through is the same the whole way. But if something splits into parallel, the voltage drop on every part is going to be equal. Another way to think about it sort of is like voltage is kind of like, if you think about electrons moving through the circuit, voltage is like the energy they all have. So, and then current is like kind of the rate or how fast they're flowing, since it's like charge over time, Q over T. So if you think about series, like they're all flowing at the same rate, but maybe you're using up a different amount of energy on each of the resistors. So like if you have 5 volts and you're going in series with 2, maybe you're using like 3 volts on one and 2 on another. So your voltage drop can be different, but all the electrons are flowing at the same rate there. Whereas for parallel, your rate kind of slows down, because if you're visualizing like physical electrons getting to a parallel point, they have to split up. So they're maybe getting slower because like every other electron is going a different way. But from when they're at this point here to when they come back here, they have to all lose the same amount of energy, if that makes sense. Like if they lost some on the one in series, you want them to lose the same amount so when they get back, they all have like the same amount of energy to finish off the circuit, if that visual kind of makes sense, or that analogy. So anyways, all that to say, the voltage drop has to be the same in the parallel section. And so what that means is you can already solve for the drop here because V equals IR. And so you have your I is 2 amperes and your R is 2 ohms. And so you know that's going to be 4, 2 times 2. So then here, you know that your V, 4 volts, is equal to your I times 4 ohms. And so that means your I has to be 1 ampere. 1 ampere. Sorry for the bad writing. So then you have the sum of your 2 amperes and your 1 ampere has to be how much was going through this one, which is like the in part of the junction. So hopefully that breakdown makes sense. Another, I guess, quicker way to view it is also, since the voltage is the same on parallel, if your current doubles, your resistance halves, or the other way around, if your resistance doubles, your current halves. So you can also just look at this and say the 2 ohm one is half the resistance, so it has to be double the current. So that's like 2 amperes. If 4 ohms is double the resistance, it's going to be half the current, and then you can just get that it's 1 ampere that way, but it's based off the same principle, whatever is easier. So then it's going to be our 3 amperes. Oh, I have to clear the annotation, don't I? Okay, here's another question. If you don't know, that's totally fine. Just take a guess. Okay, so for this one, it's D, and the breakdown of this is it draws from 2 equations. So we know V equals IR is our Ohm's law, and the other one is power is IV. I think that was in the first screenshot, but basically these are the two to know. V equals IR, P equals IV, and then what you can do is combine these to get rid of the I here. So if V equals IR, you can also rearrange that as they have here as I equals VR. And then if you sub that in for I equals V over R. So if you sub that in here, this squared part here is kind of what's important to note. Power is V squared over R. And so another way to think of it is if you sub in IR for V, then you have I squared R is also power. So just good to know that these two equations can combine because it's the same variables. But the gist of what they're getting at here is that the power lost is I squared times R, and your resistance is fixed. So what they do is put a high voltage so that at a lower current, you're minimizing the heat loss. And so I guess your resistance is fixed. You put a really high voltage to lower the current so that that I squared R is very low. Hopefully that kind of makes sense. And this actually is what they do for like electrical lines and such. It's very high voltage, like the towers and stuff on the roads. And the next part is resistivity. Oh, clear. So in terms of like circuits and stuff, you'll just get kind of the resistance value, like 5 ohms or whatever. But if you were to actually figure out what the resistance is, it's based on 3 factors called resistivity, length, and cross-sectional area. And so resistivity is like inherent to the property of the material, and then length and area are based on like how you shape it. And so resistivity and length will increase your resistance, whereas area actually, higher area decreases it, so that's why it's in the denominator. You can also think of that intuitively, like resistivity is just like inherent to material. You can think of it like kind of like the coefficient of friction or whatever. It's just something you multiply there. But in terms of length and area, a longer length is harder to get through. Like even if you're thinking about yourself trying to get through a tunnel or something, the longer it is, the harder it is to get through. So that's why that would be a longer length, more resistance. That's why it's in the numerator. Whereas if something has a large cross-sectional area, it's easier to get through. Like a very narrow tunnel is harder to get through than a very wide one. And so that's why it's in the denominator. So when your area goes up, your resistance will actually go down. And then we move on to capacitance. So 2 equations for it. One is kind of like your V equals IR, where Q is CV. So your charge is equal to your capacitance times your voltage. And so that's just like if you have a parallel plate capacitor, you might have one of those like in your circuits. And then inherently capacitance is kappa epsilon naught A over D. And so all that means, so kappa is your dielectric constant, so that's like based on the material, a lot like how resistivity is based on the material there. Epsilon naught is a constant permittivity of a vacuum, so that's also going to be like a fixed number. And then the part that you should know, it's like the opposite for resistance. It's area in the numerator and distance in the denominator. Capacitance is like you're storing kind of charge within these plates. And so the more area you have, kind of the more you can store, but the distance apart makes it harder to have like the connection between the plates. You can think about it, but like the larger the distance, the less charge you can store. So that's like inherently what capacitance is, but then within a circuit, you can also use Q equals CV. Last thing, I think this is the last thing before, yeah, so we'll cut off here and put the rest in part 2. Last thing is meters, not the unit, but the way you can measure. Sometimes they'll ask you about measuring things within a circuit, and this is the difference between the 3. In real life, you're probably going to be using multimeters. You might have used them in like Physics 2 lab, where you can just turn the dial and measure everything with the same meter. But if they were to be separate, an ammeter measures current, like amperes, and it's inserted in series. So again, as I was saying, like in series, the current is always the same. So you can just put that in the middle of your circuit and it'll experience the current and like how fast everything's flowing. And it has a very negligible resistance. Whereas a voltmeter, you put in parallel, because as mentioned, in parallel, every branch will have the same voltage drop. And so in that sense, if you put it in parallel with the stuff in your circuit, it'll measure what that voltage drop is. So if you're only measuring the voltage drop across one resistor, then you can look at the picture there. That voltmeter parallel to that one resistor is only going to measure the voltage drop across that one resistor. And it has a very, very large resistance, and hence low current, so that it doesn't really bother the current moving through the other spaces. And then an ohm meter will measure like the resistance of an element, but it has to be isolated, not like within a working circuit. So you can actually just like take a resistor off and then measure resistance. It's self-powered and has a negligible resistance. So you actually have to like take it out of the circuit and measure the resistance across that. So that's the difference between the meters. I think in terms of like, you don't have to know a heavy amount of detail, but it would be good to know that an ammeter is in series and a voltmeter is in parallel, which you again might also just know from Physics 2 lab as well. So if there's any other questions, I can stay back for a couple of minutes if you'd like to stay on. Otherwise, we'll end it here and continue from waves next time, which will be not tomorrow, but Wednesday for part 2. Feel free to leave any questions in the chat or stay on. But otherwise, thank you guys for a good session.